proteins is they can fold and unfold proteins. These are protecting osmolytes. They fold proteins. That's a denaturing osmolyte. It unfolds proteins. There's water put in there as a kind of fiducial marker. All kingdoms have these osmolytes. If I go out into the desert and find a plant that exists in the form of one of these desiccated seeds that's been living there for 100 years under hot desert conditions, and you add water to it, and the plant blooms, why doesn't the plant, don't the proteins in the seed denature under those incredibly denaturing conditions? And the answer is because they have organic osmolytes, protecting osmolytes, that are packaged up in the seed that do that to the plant. When I don't drink for a while, the concentration of urea, this denaturing osmolite, concentration of urea in my kidney can go up to 2 or 3 molar. In a shark or a ray, it can go up to 5 molar. 5 molar urea is enough to denature most proteins. Why don't the proteins in our kidney denature? And the reason why is because they're accompanied by protecting osmolytes. In the shark, it's accompanied by TMAO, which is poisonous for us, but we have glycine betaine. And those are counteracting protecting osmolytes that protect our proteins from denaturation as a consequence of urea. So there's a lot of work that's been done on the thermodynamics of osmolytes, and what we know is that protecting osmolytes shift this folding equilibrium towards the end state, and denaturing osmolytes shift the equilibrium towards the unfolded state. This one is protecting. These are all protecting. That's denaturing. Here's a review article with Wayne on this whole topic. But most of the work in this area has not been done by me. It's been done by Wayne or Tom Record or others. And I'll show you some references. How is it, thermodynamically speaking, that these osmolytes are doing this? And what they know, and we're confident that we know this because it's straight thermodynamics, it's been measured. And it's been measured by a number of investigators. What we know thermodynamically, not mechanistically, is that the way they're doing it is that if you had a population of proteins under denaturing conditions, so here the unfolded state in water is lower in free energy than the native state, and you put in a protecting osmolyte, it raises the free energy of the native state, but it raises the free energy of the unfolded state much more, so that now the native state is lower in free energy than the unfolded state, and it folds the protein. Saying nothing about mechanism. And exactly the converse is true for denaturing osmolyte. It lowers the free energy of the native state, but it lowers the free energy of the unfolded state a whole lot more, so now the denaturing osmolyte can change a population in which the protein is native, the folded population is dominated, the one in which the unfolded population dominates. Again, thermodynamically, what we know is that the predominant effect is on the unfolded state, and it's exerted predominantly on the backbone. Not on the folded state, not on the side chain. So whatever osmolytes are doing, and they're doing it, and we know this thermodynamically, they're doing it to the backbone, not the side chain, and they're doing it on the unfolded state, not the folded state. And if they're doing it to the backbone, it makes perfect sense. It's plausible that if what they're doing is predominantly to the backbone, it should be also predominantly on the unfolded state, because in the unfolded state there's more backbone exposed to solvent than in the folded state. This work was done initially by Serge Timashev, and then more recently there's a paper by Matt Out and Wayne Gold. I should emphasize that in coming to these conclusions, which are sound thermodynamics, there were many, many complex problems that had to be solved along the way. And I don't have time to go into this. But doing this in a way that is thermodynamically sound turned out to be a real tour de force.
Some of you, the older colleagues in the room, remember George. Some of you younger colleagues probably just think that this is a great lecture and it's a wonderful opportunity to come and have some free coffee and cookies. Incidentally, there will be some in the reception afterwards. So, but indeed, on the screen you see a picture of George. This was taken in 1987, and George at that time was remarkably young, was only age 43, and was elected at that time to the National Academy of Science. So indeed, in a very short period of time, had really accomplished a tremendous amount, both in terms of science and some of us remember also in terms of his mentorship. So several of us in the audience, including myself, was trained by George, and we were of course very grateful for the training and his mentoring. And he was in fact a truly remarkable scientist and teacher. And some of you may recall that nowadays, when you work with sort of the DNA binding proteins, transcription factors, and enhancers, you think that they were just there. But in fact, that entire concept of enhancers and transcriptional activators was in fact originally discovered by George Corey. And in fact, in honor of George's memory, we actually started this lecture, and it was started now as far back as 1994. And during all the different episodes of government shutdowns and whatnot, the lecture has managed to persevere. So we've had a number of stars, including the very first lecture was Ani Levine's in his each meeting time. As you can see, some of the other cast of outstanding scientists would come and deliver the lecture, including Bob Weinberg, Peter Howley, Bob Tijan, David Baltimore, Phil Schaub, Bert Vogelstein, and the list goes on and on. So here I just show you some of the examples of really outstanding speakers who commonly give the Corey lecture. And today, of course, is no exception. And so, if I could, then what I would like to do is to introduce our speaker today. And he is Jeremy Nathans from Johns Hopkins. And Jeremy, of course, is also one of these young and wonderful, outstanding scientists. I think he was also elected to the National Academy, probably not much older than 43, right? Probably perhaps even earlier than that. And Jeremy is, of course, known for many of you for his work on the research in the molecular biology of vision. And he was the first person to isolate the genes that code for human visual pigments, discovered the first sequences of eukaryotic sensory receptors. He taught us the molecular basis of inherited variation in color vision, and defined the biochemical basis of different forms of macular degeneration. So vision is something that's very important to us, and I think this is something that all of us, it behooves all of us to benefit from Jeremy's work and from what he's here to tell us. My fond recollection of Jeremy was seeing him, the first week when I was in college at MIT, seeing this tall, smart, lanky, student who was in my recitation class at MIT. And, 30 years later, he remains tall, lanky, and even more smart. So, welcome, Jeremy.
Well, thank you for that very kind introduction. I think I have my own mic at this point, so I can speak like this. It's a great honor to be here, especially to give the George Corey lecture. I never met George Corey, but I feel I have a certain connection with him. He collaborated with my father, Dan Nathans, in the 1970s in SB40. And with Malcolm Martin, they mapped the first transcription maps of that viral genome. And there are a series of papers from the mid-70s which they are co-authored, which really, I think, laid out in many respects this paradigm of dissection of genes and chromosomes. And Dan always spoke of George with great affection and respect, and so I sense a certain connection even over these many years. So let me describe for you some of the work that we've been doing now on the evolution of primate trichromacy. And I want to start with two somewhat extended appetizers before we get to the main course. The first appetizer will be historical. A look at the history of television research very briefly. The second will be